teach it, but it has to do with, again, how far you can stretch the data out so that it's not redundant. And there are separate tables pointing to separate tables, pointing to separate tables. So this gives an example of first normal form. Get rid of duplicate columns from the same table. That seems pretty obvious. There's an example of that second norm. Remove subsets of data that apply to multiple rows of tables and put them in a separate table. That makes good sense. And then the third form, remove columns that are not dependent upon the primary key. And this gives you an example here that you can and walk through. And then here's an example of referential integrity with our good old friend the orthodoxy database that says, you know, if you're going to enter an order in at the help desk, that has to have a status ID, and you can't put anything you want in there. The status ID has to be one of those things, and the subject can't be anything you want. It's got to be the subject that's in that table, and the departments can't be anything you want. It must exist there, etc. And you understand that, I'm sure. And then here we go, getting data from multiple tables, using an inner join. This little footnote here, multiple joins across several large tables is quite, go away, I/O and CPU intensive operation. So if the nature of your data is that you're going to do lots and lots of inner joins, you're really going to tie up your database. So it makes you think, maybe I want to use a different structure than a SQL database, or probably more commonly, what you do is you break your roles and you actually do duplicate fields. You will, every time you're going to go and get somebody's address, you're going to have to then go look at the city table and the zip code table, and you're really trying to get performance. You say, the heck with it, and you get rid of the city and the other one. Well, you don't really get rid of them. You use them in a different way. And then every customer has the real city and zip code in their record. That way you don't have to do an inner join when you want to get a customer and print out their record. So you start violating your own normalization rules to trade off performance to avoid inner joins. So why isn't all data stored? They're normalized for fast data insertion or updates because that will affect the fewest number of columns and the fewest number of rows in a single record. So you want to insert a new customer, you already got that city in the data, you already got that zip code, you already got that street. You don't have to go update those tables. All you have to do is hit one record and have all those secondary keys. And then simple queries like what's Zach's phone number is really fast. But high insertion rates affecting multiple tables is not optimized, and that's why we have this thing called big data and or NoSQL. And then complex queries such as, tell me all the married women in the state of Washington with 2 or more children who have earned a college require. It may cause the database engine to go cycles after cycles after cycles, going through all the tables and matching them and filling up memory with all this partial data. So that's why BI cubes were invented. And then we also have this problem, which is company A wants to do business with company B, and they have completely different database implementations, and their data stored in completely different tables, right? So that's where using XML for data exchange comes in really nicely. Because I can read the XML file and then automatically code that to an insertion in my database, and so can the other company, even though the databases are completely different. All right, a few words on what is a multi-dimensional database. again, whenever I put a web link in there, it means one of two things or both. It means I stole information from them and I'm giving them credit, and or if you want to read more, you can go to that web link. So multidimensional databases, I will typically just say Tues as a shorthand way of saying it. It's a database that's designed for what's called analytical processing applications, OLAP, online analytical processing. And before you read all that, I'll give you the classic example. You're checking out of Target, okay? And you hand them the credit card, and that company at that moment wants to sort of go to you and say, you know, we're having a special on dog food for dogs with diabetes. Do you want to go back and get a few bags, right? You go, how the heck did you know that? Well, because they got a big BIQ back here that has all their customers and all your buying patterns and everything you ever bought. And they want to run a query like that in the time it takes to talk to a human being that says, what should I be offering that customer? And that's the kind of thing that is done with these things, because they're set up so that in one query, they practically instantly give you back that data. They're optimized for that one really fast query. And when you build them for a certain set of queries, if you try to ask a query that doesn't match what you built it for, they're horrendously bad, or you can't even do it. Okay, but you design a BIQ with a very specific sort of mining goal in mind as to how you want to mine the data. So most times you'll have production database, like Target will have real database machines that every time you're buying items, they're going into a SQL database, chunk. So they're keeping track of you and what you bought and what everybody bought, and what their inventory is being changed because they can see you bought stuff, right? And then several times a day or once a week or once a month, whatever, they will pull the data or some snapshot of the data, like maybe the last 2 weeks' data, out of the SQL database, and then they'll load it into this BI database. Okay? And then this loading process, in effect, does the pre-joins automatically and structures the data as though you had done the joins, so that now you can ask a question like that. I don't get into it much, partly because I don't understand it, partly because I don't think it's right for this course, but one of the things Microsoft has done, and Microsoft is doing pretty well with BI, is people have done amazing things with spreadsheets in Microsoft Excel. I mean, Microsoft Excel is a very, very deep product that you can do. You can run a business off of it all by itself. You don't need anything else. So it turns out there are a lot of people that understand the concepts of mining for data by creating queries on their spreadsheet, and they know how to do that, right? So one of the things that Microsoft has done is they have married the front end of Excel, and then you connect it to a BIQ, and you get all the people who know how to do spreadsheets well, all of a sudden are data mining experts now, only instead of playing with a relatively small Excel database, they can be playing with a 20 gigabyte BIQ. So OLAP usually has 3 operations: consolidation, drill down, slicing, and dicing. So consolidation means you go through all the data and you accumulate it and put it into what are called dimensions. So here's an example. All sales offices are rolled up to sales department or sales division, so you can look at what the sales trend is. And this is called a cube. Drill down is a technique that allows you to navigate for details. For instance, user can view sales by individual product that makes up the region's interest. And slicing and dicing is when you can take a slice of a specific piece of data and look at it from different viewpoints. And I think I have a picture of that. I'll get to that in a second. Okay, MDP in support of OLAP. It is common with multidimensional databases to use what's called a data cube. Now, it's kind of easy if you think of a data cube as being a 3-dimensional thing, but And some cubes are cubes, but most cubes are not. Most cubes are four-dimensional, 5 or 6 or 7, okay? So every time you see the word cube, you really should just be thinking multi-dimensional. But learning it and trying to visualize it, I think it's perfectly reasonable to think of a three-dimensional cube because it's a lot easier to understand. So here's an example. We have internet sales could be a fact table, which is called a measure, where sales activity is stored as facts, as data. Okay, so you're pumping in real internet sales that you've actually have. And then you can interrogate that across dimensions, such as what do my sales look like by geography, or what do my sales look like by time, or what do they look like by product? So you would load the cube up with the fact table, which is the facts. What did you actually sell? And then you would design this particular cube with a specific goal in mind to basically have 3 dimensions. And again, the 3 dimensions here are geography, time, and product detail. And then it makes it really nice to analyze as you think in those dimensions. And then often, any one of those dimensions has subcategories, like you could break time down into, give me everything for the last year, or show me the last 4 quarters, or show me the last 6 months. You're just cutting down one of the dimensions, that's all. And here's the thing, they're usually quite denormalized. They're the opposite. They repeat the data all over the place in order to make it very fast. And then you use something like SQL Server Integration Service to keep, and again, this gets into how much you want to spend and how desperately you want the data. So you can load the data every 2 hours and keep track of data for the last 2 years, which would be pretty expensive, or you can load the data once a month and keep track of only the last 2 months, and then you wouldn't need so many gigabytes of storage. So you can imagine the big companies have huge systems, and small companies probably have to make some compromises there. So what is a fact table? A fact table is real data. It's something you actually measured. The fact table is larger than the dimension table, which means when you take a dimension, it's by definition, it's a subset of all the data, the fact table. It has foreign keys that refer to primary keys in the dimension tables. And the dimension tables are descriptive attributes that are usually textual. And that gets to what I just said up there. So you load up all the sales and then you say, well, show them to me by geography. So here's a simple example. So this one has sales as a measure, which would be a fact table. Okay, so the fact table has literally the actual sales that you actually do. Now, of course, there'd be more fields than this. This is just like a subset of the fields. But you're creating a unique key for each item that goes through the cash register. You're recording what the amount was, what time it happened, what product it was, and on and on and on. And you're cranking that out, okay? And then you can, off of that, you can build a time dimension, which is keep track of every unique timestamp that was generated here. Okay, so these are time IDs, and this is going to be, this now shows you every time event that something was purchased. And then here's a product dimension, which would come along and would keep track of every product that was bought. Like, what is that product? Oh, that's the product. What is its description? Blah, blah, blah. So this is 2 dimensions against all that facts. So given that, you could say, by looking at this one dimension, you could say, when are my stores the busiest? How many salespeople should I have working? And you can do beautiful plots that'll show over time how your business is going, looking at that dimension. Or you could say, you know, which of my products are selling well? And then you can do that. And then, of course, you can do things like which products sell really well during this time period. So a rake makes a poor shovel. So just reiterating, relational databases are simple, but they can't run complex queries and they can't do really fast updates. So here's another picture of a multi-dimensional one. So imagine that you're keeping track of every time you have a test, what each student got, what their score was on each of their tests, okay? So the facts are, every time you're running a test, you're loading up the fact table with which test it was, you know, was it exam 1, 2, 3, or 4, and which student it was, and what their score was. So now using that fact data, you can build a 3-dimensional cube, and now you can analyze and say, well, how did my students do on exam 1, exam 2? You could say, how did this student do across this set of tests? And, you know, how are my results looking like? Are students generally getting better than a 75? So hopefully that gives you some slight gut feel for what we're talking about here. Do you dare ask a question? Is it making any sense? Okay, so 4-dimension, like I said, they can be as big as you want. What do I say here? It's hard to draw a picture, but in this example, I'm adding a 4th dimension called subject. And now you sort of, it's like you have 3 cubes, and then you pick, this is the cube for databases, this is for programming, and that's for software engineering. So I don't know if that helps or not. Visualizing 4 and 5 and 6 dimensions is a pretty hard problem. I got really good grades in calculus when I went to college, and then I took an advanced and I went into n-dimensional calculus, and I was totally lost. It was so easy to imagine calculus in 3 dimensions, but 6 dimensions, I couldn't do it. So again, the advantages of multi-dimensional over relational. So if looking at the student exam result, assume the rate of change of data is not extremely high. You know, you don't have thousands of students taking thousands of tests every minute. And the primary use of the data is to analyze it, not change it. You're not going to go back and change the students' scores or invent a test that never happened. So there are reasons why it's more efficient to store it in multi-dimensional rather than relational. All similar information is lined up in a single dimension, like results. So the data can quickly be summed for totals or compared to get an immediate idea how they're doing. The multi-dimensional array has a higher level of organization, which is the opposite of being normalized. So it destroys some of the obvious relationships among some of the columns. When you force it into that model, in the underlying SQL data, there could have been relationships, but they're gone because you've broken it by putting everything in these long linear tables. Well, it says the structure is more intelligent view of the data. Well, it's more intelligent as long as you confine yourself to questions that fit the dimensions you picked. On the other hand, like a SQL implementation, you can walk up to it and ask any question, and you can figure out how to do multiple joins to get the answer. Once you've built a BI cube along certain dimensions and you've lost those relationships, it's really good at some questions and it can't do the other ones. So if we design a relational table for students, it might look like student name, exam, results.